All right, today, so we're going to do inverse exponential logarithms, but we'll go over that one problem from last week here, from last time we met. So is asking you to graph those equations? Okay, so with graphing, with an exponential, I mean, this is often the best way to go in terms of figuring out how something is going to graph. Excuse me. So again, exponential function, how do I know it's an exponential function? When I'm looking at it, I can see that the exponent has the x. That's how I know it's exponential function. So when we have exponential functions, we usually have either an exponential growth or an exponential decay. And the way I know or can decide which one that is if, and I'm just going to write it like generically, a to the x power. So if a, let me write it like this. If a is between 0 and 1, it's decay. All right. An exponential decay in a very generic, I'm not going to actually graph, it looks like this. So it's starting up high and then going down low. That's what a decay function looks like. If it's growth, it's going to look like this, where it's kind of going up. All right. If a is greater than 1, it's growth. So anything over 1. So in both of these cases, 1/4 and 1/4 and then with a negative sign, they're both going to be decay functions. So when I graph it, I know it's going to be going down, sloping down towards something. All right. So when picking x's, I mean, the common thing we usually do is -2, -1, 0, 1, 2, and then see what happens. If we do -2, we're putting a -2 in here for the exponent. So this would be 1/4 to the -2 power. All right. Negative power means, well, essentially with a fraction we flip it. Negative exponent usually means when we have a negative exponent, it moves the other side of the fraction bar. So it moves, here we go. Why did it erase my 2? There we go. The negative means the 4 will go to the numerator, the 1 will go to the denominator, and that's the same as 4 squared, which is 16. All right, you can plug it into a calculator too, go 0.25, and then raise it to the -2 power, and you would get the same answer as 16. So then plugging in -1, -1 it flips, this will be 4. I don't know why I switched colors. 4. 1/4 to the 0 power. Anything to the 0 power is always 1. Take the 1. 1/4 to the 1 power is 1/4. 1/4 to the 2 power, 1/4 squared is 1/16. So now when I go to graph, we'll go like this, like this. 1, 2, 3, 4. 1, 4. 1, 2, 3, 4. -4. Furthest back I went was to -2. I look at these pairs. When x is -2, y is 16. So x is -2. Need to label my axes here. This is y. This is x. So at -2 comma 16, I'm over here at -2, and then I got to go all the way up to 16, which is probably off my screen, but we'll make it right there, way up high. Then I have -1 comma 4. So at -1 up to 4. There's my dot. When x is 0, y is 1. When x is 1, it's at a 4th. So at 2, it's at a 16th. If I went to 3, that would be 1/32. All getting really close. So then it's coming down, curving, and getting really close to the x-axis. It just keeps getting closer and closer and closer and closer. Exponential decay. So it'll never actually get to 0. It just becomes infinitely close to 0. So then this graph,
wouldn't it be the opposite?
it's the exact same graph except all the y terms are negative. So my t-table here xy, my pen is not running low on battery. -2, -1, 0, 1, 2. This would be -16, -4, -1, -1/4, -1/16. So when it is graphed, it's coming at it from exactly that side. So it's the exact same graph, it just gets reflected over the x-axis here. So again, the first step was we switch the x and the y, and then 2, solve for y. This would be the inverse function of that function.
You don't want us putting it into a decimal, right?
No, don't put it as a decimal. Leave them as fractions. If a question asks, here's 2 equations, are these inverses?
Yes.
One process of figuring out if they're inverses is you take this equation and work it out to see if you get the other equation. The other way would be if we said this was f of x, and if we said then this is g of x, if we do f of g of x or g of f of x, do either one of those, if this equals x, then this would also equal x. Then they'd be considered inverse functions. So if you take f of g of x and you get an answer of just x, that meant that the 2 functions are inverse functions. So to verify if they're inverse functions, either take this and do it like we just did and see if it's the other function, or take one function, substitute it into the other function, and if it comes out as x, then we know that those are inverse functions. Sometimes this is easier, sometimes this is easier. It depends on which kind of an equation you get. So today we have exponential growth and decay. Here is a broader view of what that is when we're talking about things, and we'll do one related to investing, interest, things like that. In this equation, C is a constant, R is the rate. Now when I say R is the rate, if they give me a rate of 2%, this equation is the rate in terms of decimals, not in terms of percents. Because that's a decimal, this is a decimal, these are all decimal numbers. So I can't use percent, so you have to become, get back familiar with how do I convert 2% into a decimal. So 2% as a decimal is moving the decimal place 2 places. Percent means out of 100, moving that decimal 2 places. So my R is equal to 0.02. Again, getting comfortable and confident with converting decimals to percents. If the rate was given to me as 2%, then that goes in here as 2, or in here as 2. So if I have 2% growth, it's 1 plus this, and it would be a 1.02 growth rate. If it's declining, or like financially, like recession, that kind of stuff, it's going down, it would be 1 minus 0.02, so my rate would be 0.98. Like I said in one of those previous slides, whatever is being taken to the exponent, if that value is over 1, it's growing. If it's less than 1, it's declining or decaying. So now we're going to look at this one. If 2,000 is invested in annual growth, the minute it says growth, I'm going to write down that equation. Y equals C times 1 plus R to the X power. The C is the constant. It's usually what you start with. In this case, it's the $2,000. I'm going to have 1 plus R. So I got to look up to the equation and say, well, what's my rate? The rate given was 11%, but I need that as a decimal. Move the decimal place 2 places. So it's right here, and it goes 2 places over, 0.11. That's my rate. So 1 plus 0.11 to the X power. And now here's where it's like, all right, to the X power, what is the power? The power is going to be time in this case. So it's going to be per year, so 9 years. So my X is 9th power. Y equals 2,000. 1.11, just went ahead and added 1 plus 0.11 to the 9th power. And now it's calculator time. PERMDAS, parentheses, we just did. Exponents, we need to do 1.11 raised to, I can't type it in the right way. 1.11 raised to the 9th power is 2.580366924. I'm not going to write that number down. I'm just going to keep my calculator and then go times 2,000. That number is 5116. Now we're doing dollars and cents. So we're going to go to the nearest hundredth. So if you invest $2,000 with 11% interest over 9 years, after you essentially doing nothing with the money other than letting it sit there, it has over doubled. Now, 11% is a pretty good growth rate. So if you find something that's growing at that rate, invest. I highly recommend. All right, so here's a question, not related to this, but let's go some biblical integration. How is investing similar to gambling? How is it different from gambling? All right, so now, what if we're in a recession for the next 9 years?
Goes down.
It goes down, so there's a 4% loss. So we're going to write down the equation, y equals c 1 minus r to the x power. All right. C was still 2,000. 1 minus, and then I look and say, all right, what is my R? That's 4%. As a decimal is 0.04. So it's 1 minus 0.04 raised to the 9th power because it was 9 years. So 2,000 times 0.96 to the 9th. So I did my parentheses, and then we go to the calculator. 0.96 raised to the 9th. 0.6925339958, which of course I'm not going to write down. I'm just going to go times 2,000 equals 1385.07. Go to the hundredths because we're talking about dollars. So a 4% loss over a course of 9 years, not quite halfway down from what you had originally had.
They're basically still making.
Right. So now, logarithms and exponents. Most of the time we get to this part of the class and I talk about logarithms, and I either get people who go, what is a logarithm? Logarithm. Or people say, I hate logarithms, or I never understood logarithms, or all sorts of variations. Logarithms and exponents are the same thing. They're just written differently. So here I have an exponential function, y equals 5 to the x. 5 is my base, x is the exponent, y is what it equals. This is the exact same thing as this, it's just written with logarithms. 5 is the base, x is the exponent, y is what it equals. So how we're going to use it is we're going to be trying to solve now in the future for x. X isn't an exponent. So I don't know what, like, is it a square? Is it a cube? Is it a cube root? Like, I don't know what the power is. But to do that, what I'm going to do is what's called a logarithm. So like in this case, if I wanted to, solve this, I can convert an exponent into a logarithm function because, and again, the exponent is what it's going to equal. X, here it's also x, and we'll do this. The base is 89 or 0.89, so that's the base of my logarithm, 0.89. And we'll do some of these in a minute so we understand what I'm talking about when I get to there. So then here I have this. I'm like, all right, I'm going to convert this into a logarithm. My base is 4, so it's log base 4. The exponent is 3, so that's what it's equal to outside here all by itself. And what's inside parentheses is what the original equation was. So here, the original equations were equal to y, so that's what's the logarithm of y. Here it's equal to 64, so it's a logarithm of 64. In this case, my base is 4, so it's log base 4 of what it had been equal to equals what the exponent was, 1/3. So again, logarithms and exponents are the exact same thing. What you're going to want to get in the practice of doing is converting it from one to the other. Can you go, or if we're given this, can I convert this into an exponent form? A couple more examples here. Log base 5 of 25 equals 2. So to convert that into an exponent, its base is the 5. That's the log base. So that's my base over here, base 5. In this scenario, so this is the base. This is the base. This is the exponent. This is the exponent. This would be, in this case, when we're thinking this would be the solution or the answer or what it equals. And when I'm converting it to here, that's where that goes, what it equals. There's the base. There's the base. This is the exponent. This is the exponent. What it was set equal to, what it was set equal to. Again, showing this just as a converting it one to the next to the next. So if we're going to do this, let's look at this first one here. And I have it set equal to nothing. It's an unknown. So just call that x. What is the base? 3. What is the exponent? Nope. It's the x. And then what it is equal to is the 9. So it goes base raised to the exponent equals that. So just out of curiosity, 3 to what power is 9? 2. All right. Next one over here, we don't know what that one is. We'll call it, and again, it doesn't really matter, r, so we're not using x again. What is my base? 2. Which one is the exponent? The r. And then it equals 8. 2 to the what power is 8? 2 times 2 is 4, times 2 is 8. Nope, not 8. R is 3. 2 times 2 times 2, that's 8. So again, just converting one back to the other. What is my base? 2. What is the exponent? Y. What does it equal? 1 over 8. This one gets a little bit more difficult, so I go, well, I know 8. We just did this one, right? My thought bubble. That's 2 cubed. So if I have 2 to the y equals 1 over 2 cubed, I'm like, well, I'm close, but I need this 2 to be in the top. Is there a way that I can do that knowing my rules of exponents?
Can you make it a negative?
Yes, can make it a negative. So this is the same as 2 to the negative 3. If I just move it to the top, that changes the exponent from, well, whatever it was. In this case, positive to negative. Like we did when we started class today, and we looked at that in the negative exponents. Negative exponents just move it to the other side of the fraction bar. So now I have 2 to the y equals 2 to the negative third. Well, that means y is negative 3. If I have a logarithm, I can convert it back to exponential form. What is my base?
5.
5. Which one is the exponent?
3.
3. And then it equals x. Again, it's 5 to the third power equals that. So as you're writing notes about things, it's one thing to write it down one step to the next, but like what's going on in between there? I'm asking the same questions. 5 is the base, to 3 is the exponent, it equals that x. And then you can cube that and say 125 equals x. So sometimes we'll have questions where it's easier to convert it out of the logarithm into an exponent. Sometimes we'll have problems where it's going to be better to take it from an exponent, make it into a logarithm. Properties of logarithms. Log base b of 1 is 0 because b to the 0 power is 1. B to the 0 power is 1. Anything to the 0 power is 1. B log base b of b to the x equals x. Because over here, what it means is b to the x equals b to the x. I mean, that's kind of like the identity. B to the log base b of x equals x. So this is an exponential form. If I were to convert that to logarithmic form, what is my base here? Now it's awkward because there's a lot going on. So this is b to this whole power equals x. So just imagine this as just a blob. B to some power is x. What is my base in that scenario? B. This b right here is the base. Base to some power. So the base is then log base b. Okay? Right? B to the exponent. Which one's my exponent? That's my exponent. So b to the this power, so the power goes over here. This is my log base b of x equals what's inside, which is x.
So it just means the exact same thing.
Yes. Yep. So if I were to convert this exponential form into a logarithm, you go, so if I gave you this, log base b to the x equals log base b to the x, you go, well, yeah, that's what that is. This is going to be one of the most important things that we're going to be using to solve. Because if we're trying to get rid of a base or a log, we're going to oftentimes use the inverse to get there. More properties of logarithms. This is like these are properties of exponents as well. Remember properties of exponents? If I have the same base and I divide, I subtract exponents. This logarithm, now you're going to see me write logs without any bases. If there's nothing written, it is commonly understood amongst all mathematicians that it's log base 10. Log base 10. Log base 10. So same bases and multiply, we add exponents. So in logarithms, it's the same idea. If I have the same base and I'm multiplying, I can rewrite it as addition of the two different things. And the reason why is because 10 to the a power times 10 to the b power is 10 to the a plus b power. This phrase and this phrase are the exact same thing. This is written as an exponent. This is written as logarithms. If I have same bases and I'm dividing with exponents, I subtracted the exponents. So same bases, log base 10, and dividing, I'm actually subtracting. And then powers raised to powers multiply, which means that power essentially moves out and sits in the front. So now I have b times log base 5 of a. And when in doubt, if you're ever like, I can't remember all those properties, I mean, a quick Google search and it'll show you like images, like, oh, here's a little image of all the properties of logarithms. Just like properties of exponents. So we're going to write this as a single logarithm using those properties that we just talked about. All right. Order of operations is, well, it's going to be harder to explain it that way. When there's a number out in front, that number out in front is an exponent. Powers raised to powers, I should say. This can be rewritten as log base 6 of 3 squared. That 2 is actually the exponent. So that was one of the properties we had. And that's powers raised to powers. I can do the same thing with the next one. Plus log base 6 of 2 cubed. Do I have to write the parentheses? No. So here I did not. And now I look and say, wow, I have same bases. They're both log base 6. Same bases and adding, just like exponents, same bases and multiplying. So this can be rewritten or combined together into 1 log base 6 of 3 squared times 2 cubed. Or just, let's see, 3 squared is 9, 2 cubed is 8, 9 times 8, it would be log base 6 of 72. So we're not going to actually figure out what that equals. We're just going to leave it just like that. We will talk about how to find out what it equals, I think, next time we meet. Practice another one. Now there are no numbers out in front. So I'm just going to look and say, so they're all same bases. Same bases adding with exponents was multiplying. So these two can combine into log base 3 of 18 times 2. And then I have minus log base 3 of 9. All right. Minus, when we had exponents, meant that we were dividing. So these two combine into log base 3. So I'll have 18 times 2 on the top, 9 on the bottom. And I heard someone shout out 36 when we did 18 times 2. I would recommend, in many cases, wait till you get them all together, then start simplifying. Because now I look and say, oh wait, 9 and 18, well that's 2. So it becomes log base 3 of 4. 2 times 2 is 4. All right, this one we're going to do it the other way. We have one logarithm, and we're going to write it out as multiple logarithms, all with the same base. So I'm going to look at this and say, well, I've got dividing. Well, that means it's subtracting. So I'm going to start with log base 4 of whatever's in the numerator, 5 times 7, over, which is subtracting, log base 4 of 4. So this divided by this means subtraction of 2 logarithms. Here I have multiplying. Multiplying can be split up as addition. Log base 4 of 5 plus log base 4 of 7 minus log base 4 of 4. Bless you. And then the last thing you could do at this point, again, these are exponents, right? This would be like saying 4 to what power is 5? I don't know that one off the top of my head. It'd be some kind of a decimal. 4 to what power is 7? Again, I don't know. 4 to what power is 4? 1. So this is equal to 1. So this would simplify one last step, log base 4 of 5 plus log base 4 of 7 minus 1. And then that would be done.
If we wrote it in decimal form, is that okay too?
Right, what in decimal form?
So you know how
All right, and so what was that? That was log base 10 log base 4 of 5. So I'm jumping ahead here. This will be actually the next lecture we do. But there is a way to convert that into something I can actually use. It would be taking the log of 5 divided by the log of 4, and now they're both base 10. So to do that, I would have to be on my calculator, and I take the log of 5 and then divide that by the log of 4. And on my calculator, that gave me 1.16. I mean, 0.964,047. There's a lot more decimals. But if I tried that, I could do 4 raised to the 1.16 power. So if I did 4 to the 1.16, again, because of rounding, it's 4.9933. Right? We wanted it to be 5, but because I rounded here, I think this was 0.9 something after that. So if I did it there, I'd get more 9s, getting close to what 5 was. But we'll do more of that next time we get together. There are many examples here then of going through converting from exponential to logarithm, logarithm to exponent, and then separating them out. You get towards here, and then some of these, rewriting them using the powers or the properties of logarithms. All right. And then next time we meet, we'll actually start solving these for logarithms and exponents and some more complicated questions that go with that.
This wasn't solvable?